Hello everyone. Welcome to today's video on the handout from sections 9.9 and 9.10. As I mentioned in class, this is the final handout and our final discussion on Taylor-Maclaurin series, and specifically it'll be the end of our conversation about series in general. This handout was meant to be discussed throughout the course of the entire week, but due to some unexpected mishaps, we are now relegating this to sort of an asynchronous type video instead. What I'd like to do is work through a couple of the key examples inside of the handout so that you can see sort of how these techniques can be used to great effect. Some of the initial problems in this handout, for example, these first two problems we discussed in class. Similarly, we also discussed the bottom of page 1, where we were asking for values of x that provide a good approximation. And then in particular, we spent some time on page 2. Depending on whether you were Group A or Group B, I'll take this moment to fix some typos that we had in the square root function here for a Taylor series centered at 4. When I went through this with Group B, it turned out there were some typos found from what I had discussed with Group A. So to reiterate what we had discussed here, we used the Taylor table to build the Taylor series for this. And so we have n values, the nth derivative of x, and then eventually we're going to have to evaluate that at 4. And what we found is as we differentiated, if we don't differentiate at all, we had just x to the 1/2. And as we went through and computed our derivatives, we built the following table. Where I did not combine any of these coefficients because my goal is to spot a pattern. And we continued in this fashion over and over and over again using the power rule and fractional exponents. And eventually you're just going to want to keep doing this until you are comfortable enough that you can spot the pattern. Usually for me that means about the first 4 is probably good. There we go. And now that we have the first 4, we can now figure out the pattern for n. And what we had deduced was that, in fact, there were now, when n is 4, there are 4 2's on the denominator. So when n is n, we should have n 2's on the denominator. When n was 4, there were 1, 2, 3 negatives. So when n is n, we should have n minus 1 negatives. N minus 1. Now this is where I think there was a small typo. The top is a product of odd integers, and specifically it's the product of odd integers from, say here, 1 times 3 times 5 and 1 times 3 for n equals 4 and 3 respectively. And the pattern that we use to get there is going to be, well, how do we get from 4 to 5? Well, one of the ways to get there is we multiply 2 by 3. We multiply 4 by 2 to get 8, and then we subtract 3 to get 5. And it turns out that that is the correct notion here. So this should be 1 times 3 times 5 times etc. all the way up to 2n minus 3. This is one of the typos I had in Group A. The denominator is then going to be, as we had before, x to the 2n minus 1 over 2. And the key observation is that since this numerator is 2n minus 3, notice that, for example, when n is equal to 1, 2n minus 3 is a negative number. So that means this formulation doesn't make any sense. This overall pattern that we recognize is actually only holding from 1 onward. So that's the key, is that from 1 onward, this pattern is holding. Which means n equals 0 and 1 have to be dealt with separately. So we'll note here that this holds when n is greater than or equal to 2. Which means that if we go through and evaluate this at 4, and then put an n factorial in the denominator, the correct formulation for this should have been, well, the square root of x we know in general is always a c0 plus c1 x minus, in this case, 4, plus c2 x minus 4 squared plus c3 x minus 4 cubed, etc. And from this point onward, we have a pattern, which means the first two terms have to be written separately. C0 is going to be this initial value evaluated at 4 divided by 0 factorial. That's going to be just a 2, square root of 4, plus C1, which is this value evaluated at 4, which is just going to be 1/4 times x minus 4. Plus, now we get to actually use our pattern. So this won't be from n equals 2, it'll be from 2 to infinity. And we're going to have the coefficient, which is negative 1 to the n, 1 times 3 times 5, all the way up to 2n minus 3. All over, we would have here a 2 to the 3n minus 1 times n factorial, multiplied by, of course, x minus 4 to the n. And so if you're in group A, there were a couple things missing here, and that was definitely something that I had overlooked. But compare and contrast your work with what we have here, and hopefully you can spot the difference. Moving on from this example, we did have this find the value of the sum type problem, where this negative here is not a typo. And the key thing to realize here is that since the denominators are factorials of just 1, 2, 3, etc., we know that what we're looking for here is we're looking for the use of e to the x, which is the sum from 0 to infinity of just x to the n over n factorial. And if we expand that, we get 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And what we see is that if we take just these first two terms and we subtract them to the other side, what we're going to get is e to the x minus 1 minus x is now equal to x squared over 2 factorial plus x cubed over 3 factorial, etc. This is useful because from this point onward in the desired sum, we see that we have exactly the same formulation here as we do here, just when x is equal to the ln of 2. So what that means is that this overall sum is just 1 minus the ln of 2 plus, specifically, x squared over 2 factorial plus x cubed over 3 factorial, etc., evaluated when x is equal to the ln of 2, which we see here is equal to 1 minus the ln of 2 plus this equivalent formulation, which is e to the x minus 1 minus x, evaluated at x equals ln of 2. And you can verify that if you go through and compute this, you should be getting 2 minus the ln of 2 as our final answer. There's no reason this has to be done with strictly numbers, however. We could have done this, instead of it being one single number for the sum, it could be a unique looking series. And so the key observation to make for this particular number, this particular series, is that again we have factorials in the bottom, so that tells me that there's going to be an e to the x going on here. And so what we want to do here is we want to figure out sort of what the e to the x has to be looking like. And we'll recognize, for example, that if we were to, no, first of all, it's alternating. So we know there should be a negative running in the background. And we see here that we have powers of 2, which means there should be a 2 inside of a power as well. The only thing that's weird is that the powers have all been increased by 2. The exponential, as we see here, usually has the power and the factorial match. So what we can see is that this series is actually equal to x squared times what? 1 minus 2x plus 2 squared x squared over 2 factorial minus 2 cubed x cubed over 3 factorial, etc. These all have the same powers, so this is the same as x squared times 1 minus 2x over 1 factorial plus 2x squared over 2 factorial minus 2x cubed over 3 factorial, etc. And we witness that that's just going to be now x squared times the sum from n equals 0 to infinity of what? Well, we need an alternating component, and we have powers of 2x here over n factorial. But we recognize that this sum is just e to the x evaluated at e to the at negative 2x. So this is just going to be x squared e to the negative 2x. And that's our final answer there. This can take a little bit getting used to, and if you were in Group A, then no doubt you noticed I was sort of confusing myself when I was trying to do this on the fly in class. I should have looked at my notes beforehand, but nonetheless, this is sort of a good approach to have when dealing with this problem. The next few problems in the first couple of pages are recognizable. We have, for example, here, find the Maclaurin series for f of x equals ln of 5 plus x squared, where we notice that the 5 here is really the problem. If this 5 were a 1, then we'd be in good shape. And so the way to proceed is simply make it a 1. Notice that the ln of 5 plus x squared can be rewritten as ln of 5 times 1 plus x squared over 5. Properties of logarithms says I can split at that product and make it an ln 5 plus the ln of 1 plus x squared over 5. This has a power series associated, or a Maclaurin series associated to it. And so if I just use that, this will become the series from 1 to infinity of now negative 1 to the n plus 1 times x to the n over n, where that x now is just going to be this x squared over 5. That's the highlighted feature here. X to the squared over 5. That's what goes in right there. And so if you wanted to clean this up, you could rewrite it as ln 5 plus the sum from 1 to infinity of, in this case, negative 1 to the n plus 1 over 5 to the n times n, x to the 2n. When we did an example like this previously, I mentioned that there's multiple ways to tackle this problem. For example, you could have chosen to integrate something involving 1 over 5 plus x squared, and then integrate the associated series there. There are a litany of ways to proceed with this problem, and you're simply encouraged to do whatever method makes the most sense to you. We also looked at problems like this, where we had to find a Maclaurin series for something unusual and then use it to compute a derivative at a value. The way to handle this is we find a Maclaurin series for the desired function, which in this case will require a little substitution within the cosine series and then multiplying by x squared, and then we use the Taylor coefficients to figure out what we're looking for. In this case, f of x equals to x squared cosine of x cubed is just going to be x squared times the sum from 0 to infinity. So cosine would just be negative 1 to the n, and then we'd have x to the 2n over 2n factorial, where x cubed is now the bit that goes inside of the substituted area. And the key thing is that this becomes a 6n, and then when we multiply the x squared in, it'll become a 6n plus 2. So this becomes the single Maclaurin series, negative 1 to the n over 2n factorial times x to the 6n plus 2. The fact that we're looking for the 44th derivative evaluated at 0 means the Maclaurin series is useful. Because what we'll note is that the Taylor coefficients tell me that the 44th derivative of f evaluated at 0 must be equal to c sub 44 times 44 factorial, where again, like we did in class, c sub 44 is the coefficient of the 44th powered term. That's the key. What that means is we're going to take this power, 6n plus 4, we're going to set 6n plus 2, we're going to set that equal to 44, and that will imply that what? We end up having here that 6n equals 42, and therefore n is equal to a 7. So what that means, therefore, the 44th derivative at 0 is equal to c44, which is going to be the coefficient, namely negative 1 to the n over 2n factorial, evaluated when n is equal to 7, times, of course, 44 factorial. And if you compute that, we're going to get a negative 44 factorial over, that's going to be a 14 factorial. It's a large number, but that is the number at the end of the day. So this is another example of using the Taylor coefficients to determine high-order derivatives evaluated at the center. More examples that we work through are the following. Here we want to find a Taylor series centered at -1 for the function e to the 8x. Much like the natural log function earlier in the discussion, this will just amount to a little bit of algebra. So here what we'll note is that g of x is equal to e to the 8x. We want it to be centered at -1, so we need to have an x plus 1 sitting there somewhere. So just to reiterate that, when we want it centered at -1, what that means to us is that we want a series Cn x plus 1 to the n. Currently, we do not have an x plus 1, so we're going to simply, wherever we see x, we're going to add and subtract 1. So we're going to get a -1 plus x plus 1, all within that exponent, which will then distribute into an e to the -8 times e to the x plus 1. This bit over here on the right has itself a Maclaurin series, so we can take advantage of that. And so here we're going to get e to the -8 times the sum from n equals 0 to infinity of, we're just going to get x plus 1 to the n over n factorial. We can clean that up. This is simply going to become the sum from n equals 0 to infinity, 1 over e to the 8n factorial times x plus 1 to the n. And that's going to be our Maclaurin series, or not our Maclaurin series, our Taylor series centered at 0. Centered at -1. So again, just more algebraic manipulations that get the job done. That's kind of the key takeaway here. The last example on page 4 was asking us to get some experience creating Taylor series involving derivatives. What we see here is there's a 2x to the 5 upstairs, which I can immediately pull out and rewrite this as 2x to the 5th times 1 over 1 minus x quantity cubed. And the key takeaway here is that if I were to consider a function, say f, call it 1 over 1 minus x, this is the object without the cube, every time I differentiate f, the power of the denominator is going to increase. Specifically, we're going to observe that if I differentiate f once, and maybe if I differentiate f once, I'm going to end up getting it's going to be d dx of 1 minus x to the negative 1, which is going to be a minus 1 minus x to the negative 2, and then the chain rule kicks in. This is going to be times negative 1, which will give me a 1 over 1 minus x squared. Not quite what I'm looking for, so I'm going to do it again. So what that means is f double prime of x is going to be equal to the derivative of 1 over 1, we'll flip it all upstairs, 1 minus x to the negative 2, which is going to give me negative 2 times 1 minus x to the negative 3. Again, chain rule, this is going to be multiplied by negative 1, so that's going to give me positive 2 over 1 minus x cubed. What this tells me is then that 1 over 1 minus x cubed is equal to 1/2 the second derivative of f, which is going to be the second derivative of x with respect to x of the original function 1 over 1 minus x. This is all the hard part. Now comes the easy part, which is I know a Taylor series for this, a Maclaurin series, so now I just need to do the Maclaurin series for 1 over 1 minus x, differentiate it twice, multiply by a half, and that gives me a Taylor series for the inside here. So that's going to be 1/2 times d2x dx squared, using Leibniz notation, of the sum from 0 to infinity. This is going to be simply x to the n. It's a very simple geometric series, our oldest one. And once we're here, now we want to push the second derivative into the sum, and notice that every time we take a derivative, since derivatives delete information, our index is going to uptick from 0 to a 1 to a 2, etc. We're going to lose the 0th term, and we're also going to lose the first term, because we're differentiating twice. So this is going to become now 1/2 times the sum from 2 to infinity of n times n minus 1 times x to the n minus 2. Thus, the original function, h of x, which is 2x to the 5th times 1 over 1 minus x cubed, is now going to be 2x to the 5th times 1/2 the sum from 2 to infinity, n minus 1, x to the n minus 2. This is simply going to be, well, what do we have here? The 2 seem to cancel. The x to the 5th is just going to uptick the power of x here, and so what we're going to end up having here is simply the sum from 2 to infinity, n minus 1, x to the n plus 3. Because if we're at n minus 2 and we add 5 to it, we'll end up with n plus 3, and that's our final answer. So this is a little bit of an intense problem where now we have to differentiate more than once to achieve the desired series. However, differentiation is not the only option we have at our disposal. For example, we can take a look at integrals. Here I'd like to use the 7th order Taylor polynomial to approximate the integral from 0 to 1 of sine of x squared. The key for solving this problem is, for starters, get a power series for sine of x squared. So here, the integral from 0 to 1 of sine of x squared dx becomes the integral from 0 to 1 of the sum from n equals 0 to infinity, negative 1 to the n, and this is going to be x to the power of 2n plus 1 over 2n plus 1 factorial dx, where just like we usually do, here I'm substituting in the x squared, so that's what goes in here. Notice that this is going to become the series from 0, or the integral from 0 to 1 of the series from 0 to infinity of negative 1 to the n over 2n plus 1 factorial x to the 4n plus 2 dx. Now comes the kind of sticky part. you see this series right here has powers that look of this form, which means the powers go, when n equals 0, we get a 2. When n equals 1, we get a 6. And when n equals 2, we get a 8 plus 2 is 10. So this power right here is upticking from 2 to 6 to 10 to 14, etc. Notice, though, that if what I want to figure out the 7th order Taylor polynomial, what I need is a polynomial here that has the highest power is 7. But 7 is not here. Technically what that means is that the coefficient for the power 7 term is actually 0. So if I did take this power all the way to a 7, the 7th power term would be 0, and all I would get is everything that's before 7. So what that means is that the approximation I'm looking for is simply the integral from 0 to 1 of the number of terms that don't exceed 7, which is just going to be the first two terms, which when n is equal to 0, I'm going to get 1 over 1 factorial times x squared. And when n is 2, I'm going to end up with, when n is 1, I'm going to end up with a minus 1 over 3 factorial x to the 6th. This number, this value right here is the 7th order Taylor polynomial of sine of x squared. And so if I integrate this from 0 to 1, what I'm going to end up getting is I'm going to get I'm going to get x cubed over 3 minus x to the 7th over 7 times 3 factorial, evaluated from 0 to 1, which is simply going to give me 1/3 minus 1 over 42, whatever that number turns out to be. And so this is the 7th order Taylor polynomial approximant of this integral in question. However, just as we can use 7th order Taylor polynomials to approximate things, the question is, how good is that approximation? So we can answer a similar question, which says, what if I'm given a different looking integral and someone says, aha, take the 3rd order Taylor polynomial and ask, how good is that approximation? That is, what is the error committed in that approximation? Well, we can take a look at that real quick. This is going to be what? This is the integral of from 0 to 1 of cosine, which is going to be negative 1 to the n, of the sum, sorry, from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. But the key difference, I'm going to erase here, is that it's not just x, right? Like we usually do. I've substituted in the square root of t in for whatever that variable is. Oh, these things should be matching. That's a typo. That should be a t. We don't do any multivariable in this class. And so the result here is going to be then t to the 1/2 in there, taken dt. And so the series I'm looking for is the integral from 0 to 1 of the series from n equals 0 to infinity of negative 1 to the n, simply t to the n, over 2n factorial dt. And here's the key observation, is that this Taylor series that we were taking a look at here, this 3rd order Taylor polynomial, right? This turns out to be S3 of the cosine of the square root of t series. And so what that means is that after I integrate this series, I'm going to then get, after I do this integral, I push in and I integrate, I'm going to get the series from n equals 0 to infinity of -1 to the n over 2n factorial, and then what we're going to end up getting here is an extra n plus 1 in the denominator from my integration. And what we see here is that if I took S3 inside of cosine of the square root of t and I fed that into this integral and then I integrated that term by term, it would be equivalent to now taking S3 of this series. So what that means is that if I want to estimate the error when this is approximated by this polynomial, I find that the absolute value of the error committed when using this polynomial is the same as approximating this alternating series up to S3. So this is going to be the absolute value of S minus S3, which is less than or equal to B sub 4, where B sub 4 is the non-alternating component of this resulting integral series. That's 1 over 2n factorial n plus 1 evaluated at n equals 4, which should give me 1 over 8 factorial times 5. And so the question is, what is the error? The error is only about that big. So there's a lot of different questions that we can be tasked with answering. Maybe we'll take a look at one last integral question before we embark on something new. The last integral question we might encounter is the following. Find a polynomial that will approximate this function, which is here, yes, it's a function of x, because by the first fundamental theorem of calculus, it is the integral of a t integral where one of the bounds is at x. And we're going to integrate this on the interval 0 to 1, and we want the error to be less than 0.001. The way to answer this is, of course, find a power series for this function, and then use the alternating series. Use the alternating series error estimation. So what we'll notice here is that f of x is equal to the integral from 0 to x of 1 over t times the natural log of 1 plus t, which we do have a series for. That's the series from 1 to infinity, -1 to the n plus 1, t to the n over n, dt, which by moving the 1 over t inside, this is going to be the same as the integral from 0 to x of the series from 1 to infinity, -1 to the n plus 1 over n, t to the n minus 1 dt. Now I can swap the order of integration here, and this is going to become the sum from n equals 1 to infinity of -1 to the n plus 1 over n, because those don't have any t's in it, times the integral from 0 to x, t to the n minus 1 dt. Where we witness here that the integral of this will turn into simply t to the n over n, which will give ourselves an n squared in the bottom. When we evaluate that at x, it'll just swap the t for an x. When we evaluate that at t equals 0, it dies. So this will simply turn into the sum from n equals 1 to infinity, -1 to the n plus 1 over n squared times x to the n. That's what this function f of x is actually equal to. And now the question is, what polynomial will approximate this with an error of less than 0.001? Well, this is an alternating series. So what that means is that I want to figure out if I take s minus s sub capital N, this is equal to the error by summing up to the capital nth term. I know this is less than or equal to b sub capital N plus 1, where b sub capital N plus 1 in this case is the non-alternating component of what we have here. And so I want that to be x to the capital N plus 1 over n plus 1 squared. And the goal is to have this to be less than or equal to 0.001, which is 1 over 1,000. And so the question here becomes, as long as my x value is between 0 and 1, what capital N value makes this inequality true? I think this is a fairly interesting question. And given the sort of setup that we have here, maybe this would be a good question to pause on and let you do a little trial and error and do some thinking on this one in order to come up with the polynomial that works. I think this is a good setup for that. This is also a convenient spot to stop. I'm going to start up another video, a part 2 of this conversation, where part 2 is going to have us go through the remaining problems in this handout, all of which are new and involve limits. So take a crack at the remainder of this problem we're looking at here, and when you're ready, move on to the next video where we can talk about solving limits using Taylor series.